All right, so section 4.5 is going to talk about optimization problems, and we kind of pull a lot of things that we've talked in calculus together with things that we saw in Algebra 2 and pre-calculus. This is one of those examples, optimization problems. We saw these in those two classes as max-min problems, where we wanted to maximize the area or minimize the cost, something of that sort. And the problems look more familiar to you as we get into looking at some examples today. Critical information, we are going to be given, or we're going to have two equations normally, and we want to eliminate one of our variables to get it down into one equation, one variable. We'll determine our critical points. Remember, critical points are going to come from setting the derivative equal to 0. And then we're going to double check to make sure that our values are within our domain that we're working with. So our first example, we're going to find two positive numbers. The product is going to be 192, and we want to minimize that sum. So what are my two numbers? Well, I don't know a whole lot about them. All I can do is let one be x and one be y from way back in Algebra 1. But I know the product is 192. So if I multiply those two together, I get 192. I want the sum to be a minimum. So when I add x and y, I'll get my sum. That's what I want to minimize. Notice we had two variables, two equations in here, but more specifically, what we want to minimize has two variables in it. So we can get this down to one variable by using this information that we know. I like to go ahead and solve for y so we get our equation in terms of x. Just a little nicer to work with x, I think. Doesn't really matter. So I can take this information that I know that y equals 192 over x and replace it into my y over here. So I know x plus 192 over x has to equal my sum. I go and find the derivative here. Derivative of x is 1. Derivative of 192 over x is negative 192 over x squared. And that equals my s prime. If you don't like that, remember we can bring that x to the top as a negative exponent. Then you multiply your negative 1 to your 192, gives you negative 192x, decrease your exponent by 1, and then take that x to the negative second back to the bottom as a positive exponent. So that's where we get our negative 192 over x squared. I'm going to go ahead and find my critical numbers by setting that equal to 0. I can find a common denominator, which is x squared minus 192 will equal 0. X squared equals 192. So x will equal square root of 192. That's 13 something. Square root of 192 gives us 13,856. So not a nice clean number, but that's okay. We can work with it anyway. So we don't necessarily know if this is a maximum or minimum. With this type of problem, we normally just get the minimum where we get the maximum. Oh, first of all, we got to talk about this should be a plus or minus as well. But that negative isn't going to work for us because we're looking for two positive numbers. If we wanted two negative numbers, then we'd use the negative portion of it. So that's where our domain checking kind of comes in. So we know it's got to be the positive 13.856 because we're looking for two positive numbers. Anyway, we don't know necessarily if this is a minimum or a maximum value. So what we got to do is we got to test it. And the way we test it is to see where we go from increasing to decreasing or decreasing to increasing. So my intervals are 0 because we're looking again for two positive numbers. So it's from 0 to 13.856 and 13.856 to infinity. I can test any number between there. I'm going to test 1. In between 13 and infinity, I'm going to test 15. Again, I'm going to look in my first derivative. If I plug in 1 squared minus 192, that gives me a negative value, and 15 is going to give me a positive value. So I go from decreasing to increasing. So I know that this is going to be a minimum value because I went from decreasing to an increasing interval. So it's got to be a minimum value there. So I know that 13.856 will give me a minimum for x. I can go ahead and find my y value. If I take x value, plug it in to x times y equals 192, or 192 over x. If I take 192 divided by 13.856, in your calculator, you'll end up with 13.856 again. So the two numbers will actually be the same. And you'll find that any two numbers where you have a product, the sum's going to be a minimum when they're the same number, as long as we don't do anything else with those two numbers. Got to be careful with that. Like if it said twice one number increased by the other, then they would not be exactly the same. So find the dimension of the rectangle whose area is 144 square feet and has the smallest perimeter. So drawing a figure, there's my rectangle. I know the area is 144. My dimensions are going to be x and y, or my lengths are going to be x and y. So I know that xy is going to equal 144. My perimeter is 2x plus 2y. So I can go ahead and again reduce this to one variable. So y equals 144 over x. I'm going to take that information and plug it in for my y in my perimeter equation, because that's what I want to minimize. So we have 2 times 144 over x. That gives us 2x plus 288 over x. Again, we're going to go ahead and find the derivative of this, p prime. So we get 2 minus 288 over x squared. Again, you can bring that x to the top as a negative exponent and do your power rule. Go ahead and set it equal to 0 to find our critical points. I'm going to find a common denominator, which is 2x squared minus 288 gives me 0. Go ahead and solve for x. So x squared is going to equal 144, or x is going to equal 12. Again, this is going to be plus or minus 12, but x, recall, is talking about the side length of a rectangle, so we know it can't be negative. So x equals 12 is going to be our value. Again, we can go ahead and test that if you wish. So we have 0 to 12, and then 12 to infinity. We can test maybe 1 and 13. If I plug in 1, I get a negative value, and 13 gives me a positive value. So again, I go from negative to positive. And again, it's going to be relatively the same way. If I go from a negative to a positive, that's going to give me my minimum value. So we do have a minimum. It's kind of the proof here, if you're looking for a proof. So if x is 12, we got feet, and then y is going to be 144 over that, which would be, again, 12 feet. Again, we see that they're going to be the same kind of value because, again, we're looking for the smallest value, and we're looking at a square number there. We're looking for an area. All right. This one here, not necessarily going to happen here. They're not necessarily going to be always the same. We'll see it, I think, in the next example. We're going to maximize the volume of an open box as a square base in a surface area of 100 feet squared. So the first thing I'm going to do is draw my box in. Very crude looking box, but it's a box nonetheless. Let's see. We want a maximum volume. So the volume of this, well, we have a square base, so we say x and then y high. So that's going to be the volume of it, or x squared y. Surface area. Surface area, the bottom is x squared, surface area. But we don't have a top on it, so we don't have to account for the surface area of that. But we do have 4 side lengths, so they're the same. They're all x by y high. So we'll have 4xy to add to that. And we have a surface area of 108 feet, square feet. So again, I'm going to go ahead and solve for one of my variables. I'm going to solve for y. So that gives 108 minus x squared over 4x. Come up here to my volume, so I get x squared times 108 minus x squared over 4x. My x's here will cancel. That's kind of nice. So I get x times 108 minus x squared, or 108x minus x to the third over 4. Go ahead and find my derivative. The derivative here, since I don't have a variable in the denominator, I can go ahead and find the derivative of the numerator over that denominator. So I get 108 minus 3x squared over 4. I'll go ahead and set that equal to 0. Solving, I can multiply my 4 over, add my 3x squared, so I get 108 equals 3x squared. Divide by 3, 108 divided by 3 is going to be 36 equals x squared. So x is equal, again, plus or minus 6. But again, x is a side length of a rectangle, of a rectangular prism. Can't get the words out there. So we know it's got to be the positive value of 6. So if x is 6, again, we could test it. I'm not going to. I showed you that before. We could do that if you need to. But x is going to be 6. So it's going to be 6 by 6 by my y value. My y value is 108 minus x squared divided by 4x. So I'm going to have 108 minus 36, and then divided by 24, which gives me 3. So it's going to be 6 by 6 by 3 feet. So notice here, we don't necessarily have a nice perfect cube because of the difference in the x's and the y's. All right, and we have one last one. We have a farmer has 2,400 feet of fencing. Wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. So here's kind of our pasture, and there's the river here, so we don't need anything there. So if I have x, y, and x, I don't need that, so I don't need another y. 2,400 feet is going to be the outside dimension, so we have 2x plus y is going to equal 2,400. And we want the largest area. The area in this case is going to be x times y. Go ahead and eliminate one of my variables. I'm going to subtract my 2x over, so I get 2x plus 2,400 equals my y value. Plug that in for my y into my area. So I have x times negative 2x plus 2,400. Multiply my x through, I get negative 2x squared plus 2,400x. I'm going to go ahead and find the derivative of that. So I get negative 4x plus, off the page, off 24, or plus 2,400. Set it equal to 0. So I can add my 4x over. 2,400 equals 4x, divide by 4. So 600 is going to equal my x. So I'll have a 600 by, if I plug 600 in there, I get negative 1,200 plus 2,400 gives me 1,200 feet. And that'll be my area. So that gives you an idea of where we've seen these max-min problems before and how we can throw calculus into them to be able to solve them for us. So good luck, enjoy, and if you have questions, let me know.